So the tangent line approximation of a function is a linear function that has the same value as your original function and the same first derivative as your original function at some point. I like to use lowercase p1 to talk about this since it's a polynomial of degree 1. I don't know what you guys did when you were back in calculus 2, but like we did when I used to teach calculus 2, I guess I still teach calculus 2 in the spring. I use like P1 for the first degree Taylor polynomial and P2 for the second degree Taylor polynomial and P3 for the third degree. So I'll keep that same kind of notation here. What would the formula be for a tangent line approximation of a function f centered at x equals c? So we're going to start with something you learned way back in the day when you were taking like algebra 1. We're going to talk about the point slope form of a line. And that says, if I happen to know one point that belongs to my line, and I know the slope of the line, then the way I would write this line is I write it y minus y naught equals m times x minus x naught. Like that. So that gives me a line in the plane with that slope and including that point. Well, in our case, we want our tangent line to have the same value as my original function at the point x equals c. And it should have the same slope, or the same first derivative of the function. And a lot of times we like to solve explicitly for y. And so a tangent line formula would be like this. Or, you could write it as P1 of x is equal to this. And so that's the first degree polynomial, first degree Taylor polynomial of the function f centered where x is equal to c, or you could call it the tangent line approximation. But that's going to be important today. And let me just show you really quick, because it's nice to have a picture of this stuff. It's funny, we were also talking about this in Calculus 1 earlier. But let's say I define some function, call it sine. And I want the tangent line. So let's put that in there. Let's do y is equal to, or we can call it P1 of x is equal to, what did I just say? F prime of c times x minus c plus f of c. Type these lines into Desmos, and you can see what every tangent line looks like. And the idea behind a tangent line, the part that's really important to us, is that if you zoom in really close to where the tangent line intersects the curve, then they look the same. Within this really, really small neighborhood of the point, the tangent line is a really good approximation of my actual function. If I zoom way out, then this purple tangent line is a terrible approximation of that red sine function. But at least within a tiny neighborhood, it does a good job. So that's something to remember. In exercise 2 on your homework, it'll say something like, find the tangent line approximation of the function f of x equals e to the x. And at the point x equals 0, what that means is you're going to just use that formula and say, well, f prime of x is equal to e to the x. Okay, so when I'm using my little formula here, this is going to be f prime of 0, which is e to the 0, times x minus 0 plus f of 0, which is e to the 0. In other words, my tangent line approximation is 1 times x plus 1. And then you check your answer. You go over here. You say, what if my function is y equals e to the x? Then the tangent line should be x plus 1. And that's how you check. Visually, you can tell that's a tangent line. Perfect. So that's exercise 2. Now, what if I want to find a solution to this nonlinear equation? If I have cosine of x is equal to square root of x, how do I solve that? Right? Not easy. It's not easy to solve this in any kind of analytic way. Instead, we're going to rewrite our equation so that one of the sides is 0. And there's a lot of different ways you can do this. I wrote cosine of x minus square root of x is equal to 0. You could have written square root of x minus cosine of x is equal to 0. That works. You also could write 1 minus cosine of x divided by square root of x is equal to 0, or 1 minus square root of x divided by cosine of x is equal to 0. There's a lot of different ways you can do this, but you can always do it. Sometimes left side minus right side is the easiest. And then we define a function, like this f function, where the zeros of f are the solutions of our original equation. And now we've kind of simplified it a little bit, where instead of trying to solve this equation, we're trying to find the zeros of a function. And then we're going to do this. We're going to choose any value within the domain of your function. This is what we sometimes call the initial iterate. Step number 2, find the local linear approximation, or the tangent line approximation, of f centered at that initial iterate. Then step number 3, you're going to use that tangent line approximation and solve for the 0 of the tangent line approximation. And it's not going to be exactly the same as the 0 of your original function, but maybe it's close, especially if you're close to the 0 to begin with. And then step number 4, we're just going to keep repeating this process over and over and over and over by taking the linear approximation of our actual function and finding the 0 of that linear approximation. That's actually easy to do. So let's try it. Again, step number 1, you specify an initial iterate. Step number 2, my local linear approximation, P1 of x, or my tangent line approximation is this. It's f prime of xk, right? Or we could have said c for center, but I said it's going to be centered at this xk value, times x minus xk plus f of xk. Step number 3, we're going to take P1 of, and this is what I'm looking at right here, P1 of x subscript k plus 1, and set that equal to 0. So that means taking f prime of x k plus 1 times x k plus, oh sorry, I messed up. Because right here when I plug in xk plus 1, I'm only replacing the x with that. I'm not replacing the xk. That stays the same. That's my bad. That's still xk. Okay, but I am replacing this x with xk plus 1. and this one that is xk gets to remain the same. Okay, that's what it's like to use a function and plug in a new argument. And I set this equal to 0. And now solving for this xk plus 1 is pretty easy. I would just subtract f of xk from both sides. And I would still end up with all of this f prime of xk times xk plus 1 minus xk. Then I would divide both sides by f prime of xk. So divided by f prime of xk. And then the last step is I would add xk to both sides. And that's nice. That is an explicit formula for finding the next iterate given the previous iterate. Because everything on the right side of the equation is only a function of the previous iterate. On the left side of the equation, that tells me a formula for the new one. Okay? And so this idea of using the tangent line approximation over and over and over again to repeatedly update the iterate and get a closer value for the real 0 is called Newton's method. So this is the next algorithm we're going to study. We're going to use Newton's method to find a 0 of f of x equals x cubed minus 2x plus 2, and we're going to start at x not equals negative 3. Let's do this by hand first. So really quickly. If I asked you to do this by hand on a test, in fact, I will definitely ask you on Monday to do this by hand. I would make a little table like this. And I might even make a little part where I have f of xk divided by f prime of xk. And then, of course, we're starting at k equals 0, and x of x0 equals negative 3. This is my function. What's the derivative of this function?
3x squared minus 2.
Yeah. 3x squared minus 2. So f of negative 3 would be negative 3 cubed, which is negative 27, plus 6 plus 2, right? That'd be like negative 19. F prime of negative 3 would be 3 times 9 minus 2, so it'd be 25. And then I have to divide, so it'd be like negative 19 over 25. And then I need to take negative 3 minus all of this stuff. So it would be negative 3 plus 19 over 25. And that's how I'd get my x1. And you have, the option on Monday to bring a TI-30 X2S calculator, so you can go boop, 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 and actually punch these in instead of dealing with fractions. I would really recommend you bring that TI-30 X2S calculator for Monday so that you can do this and fill out the table. But when I give you this question on Monday, I'm going to ask you to do 2 iterations. Maybe I might ask you to do 3 iterations of Newton's method, because if you can do 2 or 3 iterations, then you understand how to do it. I'm not going to make you do 5 or 10. That'd be crazy. Another thing you can do to use Newton's method is use Excel. And if you're not familiar with Excel, I really recommend Excel as like a job skill, just like practice with it so that you can get really good at using spreadsheets. Every job, no matter if you're in business or engineering or anything else, is going to use Microsoft Excel. And then we come up with the same table, right? And my starting value was supposed to be -3. My function was x cubed. Was it minus 2x plus 2? X cubed minus 2x plus 2. Okay, so in Excel, that's how it's going to look because I have to use cell B2 to reference that when I want x. And then to get the derivative, that's going to be 3 times x squared minus 2. And then I divide. And then to get my next iterate, I take the previous iterate minus f divided by f prime. So that's how I get my new iterate. And then I'm just going to drag down these cells. Again, if you're familiar with Microsoft Excel, this is the nice part, is that you write the formulas once, then you click on the bottom right corner and you just drag it down. And pretty soon, there's no more changes happening because I can tell there's zeros in this column. After like 6 iterates, I'm as close as I'm going to get. It's at like negative 1.769 is what we're converging to as a 0 of this function. Okay, so practice using Excel. Yeah?
So just to clarify, when you actually did it by hand,
Mm-hmm.
did you just write it incorrectly? Like, could you have it as +3 plus a positive fraction?
There we go.
Cool.
That's better. Good catch. I'm glad Ben's paying attention.
That was me.
Okay, so that's how you do it in Excel. There's one other kind of picture I want to show you here.
You're confused.
What? This is weird. It hasn't even been that long since I turned on the TV. It's okay. I'm going to follow this link to a Desmos thing. Oh, I should have stayed on the page. That's okay. We'll find it again. In red, you guys can see the function x cubed minus 2x plus 2. And that is clearly the 0 of the function we're trying to find. This is the geometric picture of what we're doing when we do Newton's method. Let me scrunch it up a little bit. I don't like how tall it is. I want it to be scrunchier. Make that like -16. Maybe even more, -26. Okay, that's better. So the first thing is we start at x equals -3, and then we find the value of our function, which was like -19, so it's all the way down here. And at -19, we create a tangent line approximation, which is that first diagonal black line. Notice it's the tangent line to the red curve here, and it's a good approximation there, but it starts to, depart away from the red curve as we get closer. Anyways, it gets closer. It's not perfect, but this is our first iterate at -2.24. And then at the next iterate, we calculate the value of our function. We also calculate a tangent line approximation, this black line. And we find the 0 of the tangent line approximation. We find the value of our function. We find the tangent line approximation. We find the 0 of the tangent line approximation. And we're getting closer and closer to the real thing. And then you'll see over the course of like 6 iterations, if we zoom in, that it's getting better and better. Until, eventually it's good enough. But that's the picture of what's happening here. Newton's method is successive tangent line approximations. Now, Newton's method can fail if it enters a cycle. So let's do this. Same function, right? Same function. We are going to solve this by hand using Newton's method, but even though it's the same function, we're going to start off with a different initial iterate, and that is going to end up being what creates this failure, this cyclic failure. So when k is equal to 0, x0 is 0, f of 0 is 0 cubed minus 2 times 0 plus 2. F prime, remember f prime? It's 3x squared minus 2, is going to be 0 minus 2. And f divided by f prime is going to be negative 1. So when k is equal to 1, I need to take 0 minus negative 1 to get my next iterate. Is everybody following along with me? Same function. We're starting with a new initial iterate. Let's see what happens. 0 minus negative 1 is the same thing as positive 1. What is f of 1? 1. What is f prime of 1? 1. So f divided by f prime is 1 divided by 1. To get x2, I take my previous iterate, 1, minus f over f prime. So 1 minus 1, right? What's 1 minus 1? 0. Okay, but without having to do any more work, I already know if I start with 0, my next iterate's going to be a 1, right? So here again, I've started with 0, so my next iterate's going to be a 1. And without having to do any more work, I know if my iterate is 1, the next one is going to be 0. And so this is why I say Newton's method can fail by entering a cycle. This cycle goes 0, 1, 0, 1, 0, 1, 0, 1, and it just goes on like that forever. It helps to see a picture of what's happening. So we're going to look at a picture again. This is the same function, right? But this time I'm going to move my initial iterate to be at 0. And this is what it looks like when the initial iterate is 0. Start off with x equals 0. You find the value of your function, you create a tangent line approximation, you follow the tangent line approximation down to here to find the 0. You go up to your function, you find the value, you find the tangent line approximation, you go back and find the 0, and then it just bounces back and forth forever and ever and ever. So you don't actually find a 0. We say Newton's method failed by choosing a bad starting iterate. Okay, so that's one way you should be aware of. Also, Newton's method can fail if it diverges to infinity. So what I need to do my Newton's method is this. I need to know that the next iterate is equal to the previous iterate minus f of the previous iterate divided by f prime of the previous iterate. So somebody tell me, if my function is arctangent, what is the derivative of arctangent? 1 over x squared plus 1. So I'm not going to do this one by hand, but I'll do it in Excel for you. And in Excel, I just need to go back here and change my function to be equals arctangent of x. Like that. Arctangent in Excel is just a tan. And then for the derivative, I need 1 divided by x squared plus 1, like that. And then I can just select my formulas, pull them down. And what do you notice? My iterates that are in column B here go from starting as negative 3 to 9.49 to negative 124 to 24,000, and then big number, very big number. And then it gives up because you run out of representable double precision floating point. So this is what we say Newton's method can fail by diverging to infinity. It just can't seem to find the zero, even though it's supposed to. And again, what this looks like would be like this. There is a zero of this red function, this arctangent function at x equals 0. And if I start with an iterate like x equals 1.1, look and see what happens. You can see where I start and then the tangent line approximation. It's actually getting better and better. I am converging to the 0 with that starting iterate. But what happens if I start too far away from my 0 is it doesn't converge like that, but at some point it starts diverging away. Like if I even start with 1.5, now the tangent line approximations get farther and farther from actually reaching the 0, and this is what it looks like to blow up. So sometimes Newton's method works, sometimes it enters a cycle, and then sometimes it diverges to infinity. The next thing we're going to do is we're going to open up Python, and we're going to implement Newton's method in Python with the same kind of problem. Let's see how this goes. And while I'm waiting on that to load, I don't know how long it's going to take, but we're going to define estimated errors. So we talked about actual error in a previous lecture. An actual error was saying, I'm taking my approximation minus the true value. And then we talked about absolute error. I'm going to use a different color so I don't get mixed up. Absolute error. And absolute error was a lot like actual error, except we're taking the absolute value. And then, so it doesn't really tell me what direction, if I'm greater than or less than, it just tells me a magnitude of my error. And then the last thing was relative error. And relative error was taking the absolute error, but then dividing by the absolute value of what we're trying to find. And we really care about relative error most of the time, because if we're trying to find a really big number, then maybe 1,000 isn't so much of a big deal. But if we're trying to find a very, very small number, then even, 1 in 10,000 could be a big deal. And that puts everything into perspective when we use relative error. But the problem comes whenever I try to implement Newton's method to solve some kind of problem. Like, let me open up a fresh one. And we want to import numpy as np. And then we need Newton's method. So let's define my f function to be that function x cubed minus 2x plus 2. And then let's define f prime to be the function 3 times x squared minus 2. And then we need to have a loop at some point. So we say for k in range 10. And what are we going to do on each iteration? We're going to say x is equal to x minus f of x divided by f prime of x. So we need to define x. Give it some value to start with. Maybe x equals -3 to start. And the only problem it says is I haven't even used my NumPy library. Let's give it a go. So it works. That was actually pretty easy, right? Not too many lines of code to write Newton's method. If we're really curious to see what's happening on each iteration, one thing we can also do is say print x inside the loop. And so you can see how it approaches. And if I say x equals 0, then you can see it bouncing 0, 1, 0, 1, 0, 1, like we expected it to. All right, let me take a break. Do y'all have any questions about how we just implemented Newton's method, or does this make perfect sense? Question?
So, like, if we just choose a bad number as our first number, like, is that, like, very possible? Or is that, like, a rare scenario where it bounces back and forth or goes off to infinity?
Man, that is such a good question. It is a really, really good question. Can I point you to, like, a YouTube video to watch later?
Sure.
Because it is a great question, and we might spend more time in class talking about this. But the answer is this. If we're talking about the zeros of an analytic function, so functions that play nicely, functions that have a power series, then Newton's method will always have what's called a basin of attraction around all of the zeros of an analytic function. And a basin of attraction just means if you start with a starting iterate close enough, it's going to converge. But there's no guarantee on what the size of that basin of attraction might be. The basin of attraction might be all real numbers, or it might be only a tiny, 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 tiny interval containing the 0. You just don't know. And as far as the behaviors, whether it cycles or whether it jumps off to infinity or whatever, what I want you to do is search 3 blue, 1 brown, or 3B, 1B. And then there's a channel, 3 blue, 1 brown. And what you are looking for is a video of, maybe it's playlist. Click on playlists. You know what? I do not see anything related, so let me try this. 3B, 1B, Newton's fractal, I think maybe. I think that's it. I think that's the video you want to watch. Okay, so check this one out. Check out 3 blue, 1 brown, Newton's fractal. It's kind of a long video, but I think it definitely will answer your question about how much does Newton's method not behave very well. Because the answer is, if you're close enough, if your initial iterate is close enough, it will always converge. But the question is, we just never know what close enough is going to mean. He does a good job in that video. Now, what do we need next? Let's look at our notes.
Will you ever ask us to pick an initial iteration for our own?
Yeah, you can do that. Yeah.
So if we had a question like that on a test, do we just need to know what the answer is initially to pick a value that's close enough?
So whenever I give you a test question about Newton's method, I'm not like going to grade it according to whether or not you get the answer right. You know, I'm going to grade it according to whether or not you understand how to implement Newton's method. In fact, I'll say this. On a test question, I'll tell you what initial iterate to start with, okay? You don't have to choose the initial iterate yourself on a test, because what I'm really looking for is, can you implement it correctly? And do you understand what the pros and cons are? So we were starting to talk about this while my Python program was loading. We have actual error, and then we have what's called estimated actual error. Because think about this. On each iteration of this loop, I have no idea what the real answer is. If I knew what the real answer was, then I could calculate actual error, because I need the real answer. But the problem with this is if I knew what the real answer was, I wouldn't need to do this in the first place, right? We only do Newton's method when we don't know what the real answer is. So what do you do instead? We can estimate the actual error like this. Sorry, I don't need a hat. We pretend that the previous iterate was just an approximation, and we pretend that our current iterate is the real value. And that sounds dumb, and it is dumb, but it's the best we have to work with, right? Like, for all we know, we are hoping that Newton's method is converging, and if Newton's method is converging, then xk plus 1 is as close as we can possibly get to this. Well, I can't just subtract xk plus 1 minus xk plus 1. It will always tell me 0 every time. So what do? I go back one iterate. And I find what's the difference between my iterates. If the difference is really small, then it probably means I'm getting closer to the answer. If my difference is really big, it probably means I'm pretty far away from the answer. So that's estimated actual error. And likewise, there is an estimated absolute error that you should be familiar with. Which is the same thing, but you take an absolute value and then an estimated relative error, where you do the same thing and you divide by what our closest approximation is of the real value, which we hope is xk plus 1. And again, the problem is we would love to work with actual error, absolute error, and most of all, we would love to work with relative error. But the problem is we will just never ever know what the true value is. If we knew the true value, then there would be no point in actually doing this. We would never use iterative methods. So this is what we do instead. We calculate an estimated relative error like that. Does that make sense? Okay, so let's now go back here. And on every iteration, I'm going to come up with an estimated relative error. And that's going to be the absolute value of, and this is an interesting question too, because if I want to calculate the estimated error, I need to have an x new and an x old. And so I'm going to calculate an x new, and then I'm going to say, let's update the x old. But I can't update it until after I find my error. So anyways, estimated relative error will be the absolute value of, and it doesn't matter the order which you subtract because you're about to take the absolute value anyways. I guess the way I told it to you before was old minus new, but again, it does not matter the order of subtraction if you're about to take an absolute value anyways. Anyways, let's do this. And then we can also print estimated relative error and see what that is on each iteration. And you see it decreases every time until we divide by 0, which is not good. Oh, because I started at 0, so my thing was bouncing back and forth, 0, 1, 0, 1, 0, 1. Let's start at negative 3 and try again. Okay, so let me stop printing that too. Okay. So you can see my relative error, my estimated relative error is shrinking every time, which is good. It's a good sign you're converging. What else? Let's see what our notes have to say. What is one danger of relying on estimated error? It's possible that you end up with a really, really, really slow converging method that is creating really small gaps in between your iterates, but you're still far away from the point you're trying to converge to. That's not really the case with Newton's method, because Newton's method is a pretty aggressive method. We'll talk about order of convergence in a couple of weeks, but Newton's method is pretty aggressive. In general, if you're talking about other numerical computations though, let me just give you one extreme example. What is, and you guys are gonna absolutely break my heart if you can't tell me this. What is this sum? What's the series when I add up 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3 plus 1 divided by 4 plus 1 divided by 5 plus 1 divided by 6? Do you know?
I'll break your heart. Is it 1 over k plus 1?
I see Colin saying 2, but if I add up the first 4 terms, that's already larger than 2.
Oh.
So it's not 2. This has a special name. It's called the harmonic series. And this is one that diverges to infinity. I don't know if we have a time to, in class to prove that, but normally that proof is shown to students during a Calculus 2 class when y'all are doing infinite series. This diverges to infinity, which means it never converges to a number. But if I were just naively thinking that maybe it does converge to a number, and maybe I could use the iterative method of adding 1 over k to it every time until I reach that number. Well, I don't know what the number is, so I guess I need to rely on the relative estimated error, right? Estimated error. And maybe what I'm thinking is, well, from one approximation to the next is like one partial sum to the next. And the difference between those is the next term in the series. Well, each new term in the series looks like 1 over k. And I just want to point out that as k approaches infinity, 1 over k will eventually be less than any tolerance. So if you've set your error tolerance to whatever, I don't know what your error tolerance wants to be, like 10 to the negative 6 or whatever, then there's going to be some value of k where that's going to be less than your tolerance. And you're going to stop your loop, stop your numerical method and say, I must have found my answer. I must have gotten close enough within some error tolerance of my answer. But the reality is that there is no answer. There's not something that this converges to. It diverges to infinity. And so this is just one extreme example of something that the changes between one iterate and the next get really small. And so if you're relying on the idea of estimated relative error to tell you when to stop your algorithm, then you might give you the impression that you found a solution when you actually could be very far off. Okay. So it's not perfect. Again, this is not a good idea, but regardless, it's the only thing we have. You know what I mean? Not a great idea, but sometimes for some problems, that's the very best you can possibly do anyways. So let's use Python to implement Newton's method. We're going to use a while loop this time instead of a for loop. So instead of just doing 10 iterations, no matter what, we're going to actually say, I want to define a tolerance equivalent to 6 significant figures. And so my tolerance is going to be 0.5 times 10 to the negative 6. That's how you calculate tolerance based off of significant figures. And then we're going to use that to find a 0 starting at negative 3. So let's talk about how to implement this. Go back to my Newton's method code. And then I'm going to say not for, but while estimated relative error is greater than my tolerance, do this. And that means I need to define my estimated relative error to be something. I need to define my tolerance to be something like 0.5 times my desired number of significant figures. No, sorry. 10 raised to the power negative number of significant figures. My number of significant figures that I want is going to be 6. And let's see what happens. Maybe that works. Why can't I hit play? Okay, there we go. Now I can. All right. And so what happened when I hit play? It did 1, 2, 3, 4, 5, 6 iterations through this loop. And when it was about to start the 7th iteration, the code goes back here and says, wait a minute, my estimated relative error is less than the tolerance that I described, because now it's 5 times 10 to the negative 10 power. And so we can stop, and we don't have to continue looping through any more times. We've stopped based on a tolerance looking at estimated relative error. All right, we have how many more minutes? Is it 20 more minutes? Yeah, okay, we can do this. So count the number of flops. Everybody loves counting flops. Am I right? Newton's method requires a few flops, right? For one thing, I see a subtraction. I see a division. That's 2 so far. The number of flops that Newton's method is going to require depends on what the heck your function is and what its derivative is, and how you're choosing to evaluate the function and its derivative. And so we talked about this a little bit last time too, is that like I wrote this function in not the most what is it called, flop efficient way I could have possibly written it, because I'm multiplying 2 times x and x times x times x, And maybe there's some benefit to like messing with that, but let's not worry about that, right? Let's what's the right word? Sometimes you don't want to be too pedantic, right? Let's just take a breather and just say that's good enough for this class. Anyways, the point I want to make here, and the point that I'm going to test you over, is just this. Like, Newton's method is obviously going to require 2 flops for subtracting and dividing on every iteration. The number of flops that it actually takes to calculate this will depend on what your function is and what the derivative is. And if I want to do a while loop, because I don't want to just guess at how many iterations I need, I want to only do the number of iterations that I need. It's a good idea. And calculating the estimated relative error also takes a few flops. It takes 1, 2 for subtracting and dividing. And I guess that's it. It's like 4 flops plus however many flops it takes to evaluate the function and its derivative on every iteration. So I'm not going to beat that over, too much. I just want you guys to be aware that like certain algorithms will require more iterations, but they're less complicated. And on each iteration, it requires fewer flops. Other algorithms might require fewer iterations, but they're more complicated, and so it's going to be more flops per iteration, and you've got to consider both, because the total number of flops is going to be number of required iterations times the number of flops per iteration. So as long as you understand that, you'll be fine. And then the last thing says, discuss the stability of Newton's method. So that just means not guaranteed stability, right? Because it could diverge or enter a cycle. What are the pros and cons? So that's obviously a big con, right? For one thing, it's not always guaranteed to be stable. What's another drawback of Newton's method? Another big drawback is you have to know the derivative of the function. And sometimes you might run across a situation where you don't know the derivative of a function. Maybe you only understand what a function is as a really complicated infinite series, and it's not super easy to take the derivative. Or maybe you understand a function as it's defined by an infinite product, or maybe you know a function as it is defined as the solution to a differential equation or something like this. If you're dealing with a more exotic function, you might not always know the derivative, and so that would be a case when you can't use Newton's method. On the upside, Newton's method is much faster than bisection. If you were going to compare the number of flops to calculate one of these things versus the number of flops for the bisection method starting from a reasonable sized interval, trying to approach the same degree of accuracy, or trying to approach the same estimated relative error tolerance, Newton's method is going to get there faster in fewer iterations than the bisection method. Another pro for Newton's method is we don't need a starting bracket. The way that bisection method needed some bracket to start in. And the hard part about bisection method, remember, is that the function had to be positive on one end of the interval and negative on the other end of the interval. And sometimes that could be hard to find. There are some cases in which you don't really know how to find a case where my function is positive somewhere, and where it might be negative. Because again, if this is my function, maybe I'm trying to sample points, and I find, oh, it's positive. Oh, it's positive. Oh, it's positive. Ah, it's positive. Ah, it's positive. And I'm trying to find a zero of this function using the bisection method, but I can't even get started with my problem because every time I sample the values of this function, it comes up positive again. And so you have to start the bisection method with a positive and a negative value of your function. The good news about Newton's method is that's not required. So again, 2 downsides. It's not guaranteed to be stable. You have to know the derivative. The 2 upsides are it's faster, and you don't need a starting bracket.